All right, let's dive right into this explainer and uncover how generative AI models are actually ranked behind the scenes. We see these headlines literally every week, right? New Model X beats Model Y by 15%, and it sounds incredibly precise. But behind those glossy charts and definitive numbers, well, there's a wildly complex and honestly kind of messy reality. So today, we're going to demystify AI leaderboards and figure out what's actual science and what's just clever marketing. There's this fascinating, somewhat hidden truth about this space. As the quote goes, every generative model leaderboard cites FID, clip score, and a win rate. Each number has a failure mode a determined researcher can game. So the absolutely crucial point here is that if you don't know these failure modes, you're falling for marketing, not science. You literally won't be able to tell a real technological breakthrough from a highly optimized, rigged test run.
So here's our roadmap for today. First up, the AI grading problem. Then we'll look at sample quality and FID, prompt adherence and clip, the human ground truth, how people actually gain these AI metrics, and finally, how to build a real claim.
All right, Section 1. The AI grading problem. Assigning numbers.
Imagine your model just generated 10,000 images. You obviously can't grade them all by hand, right? You need a reliable way to assign them numbers. And that brings us to a massive core dilemma. We have to judge these images on two distinct axes that very often clash. Axis 1, sample quality. Basically, does it look real? Is the lighting, the texture, the anatomy actually believable? And Axis 2, conditioning adherence. Did it actually follow the prompt you typed in? Think about it. A model might spit out a flawlessly realistic photograph of a cat. But if your prompt asked for a watercolor painting of a dog, well, it completely failed on adherence, even though the sample quality was perfect.
Moving on to Section 2. Sample quality and FID, measuring realness. So FID stands for Freshet Inception Distance. Put simply, FID measures just how similar a batch of generated images is to a batch of real images. And because it's measuring a distance, you want the score to be as low as humanly possible. In theory, a score of 0 would mean your generated images are statistically indistinguishable from the real deal.
Now, the underlying math works in 3 steps. Step 1, it takes your real and generated images and runs them through an older image recognition network called Inception v3. This extracts a massive 2048-dimensional feature summary of each image. Step 2, it plots these two pools of data, the real and the fake, as giant clouds of points in this vast multidimensional space and calculates their mean and covariance. And finally, Step 3, it computes the Freshet distance between those two geometric clouds. If the clouds overlap perfectly, boom, you get a super low FID.
But guys, here is the catch, and this is what I found genuinely concerning. Researchers can totally game this metric. Because of how the math works, computing FID on a small sample size artificially underestimates the variance. That gives you a falsely lower or better FID score. Plus, that Inception network, it was trained on a very specific dataset called ImageNet. So if you're generating things way outside that dataset, like fine art or hyper-detailed faces, the FID score becomes practically meaningless. And worst of all, researchers can literally train their models just to cater to the Inception network's preferences. It artificially lowers their score without actually making the visual quality any better. Crazy, right?
Which brings us to Section 3, prompt adherence in clip, following instructions.
Okay, so to measure if the AI actually listened to your instructions, the industry relies heavily on the clip score. This score mathematically binds the generated image and your text prompt together. Now, unlike FID with the clip score, higher is better. A higher score means the AI nailed your instructions.
Here's how the process works. Step 1. Generated images and prompts get fed into the CLIP model. Step 2. CLIP translates both the image and the text into mathematical vectors, which we call embeddings. Then Step 3, it calculates the cosine similarity. Think of that as basically the angle between these two vectors. By running these steps across, say, 30,000 images, evaluators average it all out to get a single number. And that's the number they proudly slap on a leaderboard to compare models.
Yet, CLIP has some massive blind spots. For one thing, it really struggles with compositional reasoning. If you prompt a red cube on a blue sphere, CLIP might give the image a high score just because it sees red, blue, a cube, and a sphere, even if they're completely in the wrong arrangement. There's also this weird mechanical bias where shorter prompts just naturally get higher scores. And perhaps the most common trick of all, prompt gaming. If you just inject buzzwords like high quality, 4K, or masterpiece into a prompt, it effortlessly inflates the clip score without actually improving how well the image matches the core subject of your text. It's wild.
All right, Section 4, the human ground truth. Preferences.
Since automated metrics can clearly be tricked, we ultimately have to rely on human preference as the final judge. But before we get into the human element, let's quickly translate some of this dense jargon evaluators throw around into plain English. When they say FID, they're really just measuring the distance between mathematical representations of real and fake images. Clip score, that's just text-image similarity. When they cite an ELO, they are literally using a chess rating system to aggregate which model won more head-to-head human preference battles. And you might also hear about CMMD. That's being positioned as FID's replacement because it uses those clip features and dodges some of the statistical assumptions that make FID so easy to game.
But here's the thing. Even human ground truth isn't perfect. We see massive judge variance. For example, tech-friendly annotators often prefer very different images than recruited art and design experts do. On top of that, companies can easily cherry-pick the test prompts to subtly favor their own model's specific strengths. And here is the ultimate irony. To save money, many leaderboards are replacing humans with GPT-4 acting as an automated judge. But these LLM judges are incredibly prone to reward hacking. They frequently get completely fooled by outputs that are visually pretty, but fundamentally fail to follow the actual prompt.
Let's move to Section 5, gaming the AI metrics, tricking leaderboards. Okay, let's put the pieces together. The absolute golden rule in evaluating sample quality is that your sample size, your N, must be at least 10,000. Because of how the math shakes out, calculating FID on a small sample size mathematically skews the score in your favor. So if you ever read a paper citing an FID score based on a small N, like 1,000 images, they are blatantly gaming the numbers to look better. No question about it.
And honestly, the tricks don't stop there. You've got to watch out for researchers comparing FID across mismatched image resolutions, which instantly invalidates the comparison, by the way. Another classic trick is running the generation process dozens of times, but only reporting the metrics for a single lucky generation seed instead of giving an honest average. But the most egregious of all? LO bias. This happens when a model secretly memorized the test prompts during its training phase. It isn't generating a new image during the test. It's literally just regurgitating a memorized answer like a student cheating on a pop quiz.
Finally, Section 6, building a real claim. Production eval protocol.
With all these failure modes floating around, how do we actually separate the wheat from the chaff? Well, this is what an ultimate production evaluation protocol actually looks like today. We are moving far away from easily gameable single metrics and shifting to a comprehensive four-pillar system. Just look at the absolute minimums required to be taken seriously now. You need sample quality using an FID on at least 10,000 images against the held-out set of real images. You need prompt adherence tested across 30,000 images. You need preference determined by at least 200 blinded head-to-head pairs against the baseline. And crucially, you need failure analysis, at least 50 randomly sampled outputs hand-flagged for known issues like mangled hand anatomy or just total gibberish text rendering.
Now keep in mind, executing this four-pillar protocol, that's not something you just run on your laptop over a lunch break. It's practically a massive offline inference job. Just generating 10,000 images can take half a day on a very powerful, very expensive graphics card. To survive this, engineers have to maximize throughput by batching generations aggressively, completely ignoring latency. They also cache the real inception and clip features. That way, they aren't wasting precious compute power re-extracting data from the real reference images every single time they test a new model. They might run smaller subsets just to test their code, but the full 10K run, that happens nightly.
So, what's the ultimate takeaway from this explainer? It's simple, but it is profound. A true scientific claim requires all four of these pillars working together. Any single metric reported all on its own, whether it's an unbelievably low FID score or some chart-topping LO rating, is just marketing. Plain and simple. It's a single data point that's been completely stripped of its necessary context.
Armed with this knowledge, you're no longer at the mercy of those flashy press releases. The next time you see a big model announcement, look closely. Check their sample size. Look for all four pillars. And ask yourself, are they sharing actual rigorous science, or are they just selling you a gameable number? Thanks for joining me on this explainer, and keep your eyes sharp out there.